The concerns raised by Harvard scientists about 3I/Atlas are not based on speculation alone, but on the statistical rarity of such objects. When interstellar visitors are detected, they provide a unique window into the formation processes of planetary systems outside our own. However, the small sample size means each discovery carries outsized importance. With only 2 prior detections, the chances of observing another so quickly raised immediate questions about whether the solar system is currently passing through a denser-than-expected region of interstellar debris. This potential clustering would have several implications. First, it would suggest that planetary system formation across the galaxy produces far more excess material than current models predict. The majority of matter in a young planetary disk is believed to either accrete into planets or be ejected into interstellar space by gravitational interactions. If interstellar objects are this common, then most planetary systems could be surrounded by enormous clouds of debris, raising questions about the long-term stability and safety of spacefaring civilizations. Second, such density might elevate the risk of planetary collisions on geological timescales. While the probability of a direct impact with Earth by a large interstellar body is exceedingly low, even small increases in the flux of incoming material could influence long-term climate and extinction events. Scientists are therefore compelled to evaluate whether 3I/Atlas is an anomaly or part of a larger, poorly understood distribution of material in our galactic neighborhood. Another layer of concern involves the physical properties of the object itself. Unlike Oumuamua, which lacked a visible coma, 3I/Atlas displayed characteristics typical of a comet. This included a diffuse envelope of gas and dust, which implied the presence of volatile materials such as water ice. Yet measurements indicated an unusual rate of mass loss compared to solar system comets of similar size. Such discrepancies suggest either compositional differences or physical structures not seen before. If confirmed, this would mean that planetary systems beyond our own operate under very different chemical and thermal conditions. The possibility of exotic composition led to speculation about whether 3I/Atlas could contain organic molecules or complex carbon-based compounds. These building blocks of life are known to exist in many solar system comets, but if an interstellar body carried even more diverse organic chemistry, it would support the panspermia hypothesis. This is the idea that life's raw ingredients, or even primitive microbial life itself, could travel between star systems encased in protective cometary shells. Harvard researchers have stressed the importance of capturing detailed spectroscopic data from such objects to assess these possibilities before they pass beyond observational range. The geopolitical dimension is also relevant. Interstellar objects like 3I/Atlas are inherently rare, and the opportunity to study them is fleeting. Once an object departs the inner solar system, it cannot be revisited. This urgency has fueled discussions at institutions such as Harvard about creating rapid response missions capable of intercepting future interstellar visitors. These missions would need to launch within months of detection, requiring international cooperation and pre-built spacecraft that can be deployed on short notice. The debate highlights how unprepared humanity currently is for studying transient cosmic phenomena of this magnitude. Underlying all these scientific discussions is the lingering question of artificial origin. While the majority of astronomers consider interstellar comets to be natural bodies, the unusual features of Oumuamua left open the possibility, however remote, that it could have been engineered. 3I/Atlas, being more conventional in its appearance, did not carry the same weight of speculation. Nevertheless, Harvard researchers remain cautious in ruling out non-natural explanations, particularly since our observational capabilities are limited and detection methods are biased toward larger, brighter objects. There may be smaller, less reflective interstellar probes or artifacts passing through unnoticed. In this context, the fear expressed by some Harvard scientists is not rooted in immediate danger, but in the unknown. The arrival of 3I/Atlas underscores how little we understand about the population of interstellar objects. The current models may underestimate both their frequency and their diversity. This gap in knowledge leaves open scenarios ranging from benign natural variation to more extraordinary interpretations, any of which would transform our understanding of cosmic processes. Future efforts will likely involve a combination of ground-based surveys and space-based infrared observatories capable of detecting faint, fast-moving objects at greater distances. Harvard's role in these initiatives has been to emphasize the importance of readiness. The scientific community cannot afford to be reactive. It must anticipate the arrival of the next interstellar object and prepare to extract as much data as possible. Otherwise, opportunities for transformative discovery may continue to slip away. Another factor that intensifies scientific caution is the object's physical composition. Early spectroscopic analyses suggest that 3I/Atlas is unusually reflective compared to many comets. This brightness or albedo may indicate that it possesses a surface coated in volatile ices or unusual mineral compounds not typically observed in standard cometary bodies. If its brightness results from fresh ice being exposed as it rotates, then it may simply be an unstable object shedding material. However, if the reflectivity is intrinsic, caused by an unusual surface composition, then it would represent a category of interstellar matter unfamiliar to scientists. That unfamiliarity alone creates a sense of unease, as it suggests there are materials and perhaps processes that standard planetary science has not yet encountered. Orbital dynamics also raise questions. The speed and trajectory of 3I/Atlas are consistent with an object that formed far beyond our solar system. Its hyperbolic orbit means it is not gravitationally bound to the Sun. Instead, it is a visitor passing through, one that will never return. Such trajectories provide valuable information about the population of bodies drifting between stars. The challenge is that each of these objects arrives only once, leaving only a small window of time to collect meaningful data. Scientists fear that missing details during this window could mean losing information that might not be available again for centuries. The rarity of such encounters explains why each detection brings both excitement and anxiety. Excitement at the opportunity to observe, anxiety at the possibility of missing something essential. Another angle that Harvard researchers consider is the comparison with known interstellar theories. According to existing models, interstellar space should be filled with countless fragments of rock, ice, and dust ejected from young planetary systems. Yet the number of detections so far, only a handful in recent years, remains significantly lower than expected. If 3I/Atlas is part of this background population, then astronomers must revise estimates about how often such objects should be seen. If it is not, then perhaps current assumptions about interstellar populations are incorrect, or else something selective is guiding which types of objects reach us. Both outcomes have serious implications for astrophysics and planetary formation models. Harvard scientists also consider the possibility of contamination of data or misclassification. The faintness of the object makes observations difficult, and uncertainties remain regarding its size, mass, and surface structure. Some fear that initial measurements may mislead researchers into overinterpreting anomalies. The memory of debates surrounding Oumuamua still lingers in academic circles, where some believed exotic explanations were invoked too quickly. To avoid repeating this controversy, researchers emphasize careful analysis of 3I/Atlas, but at the same time, the fear remains that being too cautious could mean ignoring truly unusual evidence. Balancing skepticism with openness is one of the central intellectual challenges in studying interstellar objects. Beyond the technical considerations, the larger fear stems from what interstellar visitors represent. Each object carries information about environments far beyond our solar system, conditions shaped by alien stars and planetary systems. If 3I/Atlas contains materials or structures not compatible with natural formation, then it would point toward processes beyond current knowledge. Some even entertain cautiously the remote possibility that such objects could be artificial in origin. While this remains speculative, the absence of definitive evidence either way ensures that the debate remains unresolved. Harvard's scientific community emphasizes the need to approach such ideas with rigor, neither dismissing them prematurely nor accepting them without clear proof. The potential risks are not only intellectual, but also existential. An interstellar object, by definition, moves at high velocity relative to the solar system. Even a modest-sized body traveling at such speeds could release enormous energy if it were to collide with Earth or another planet. Though the likelihood of a direct impact from 3I/Atlas is effectively zero given its trajectory, its presence is a reminder of the vast number of objects moving unseen through interstellar space. Harvard astrophysicists fear that the solar system may be more vulnerable to interstellar encounters than once assumed, and each detection reinforces the urgency of improving planetary defense measures. Another layer of fear arises from technological limitations. Current telescopes barely detected 3I/Atlas before it began to fade from view. This means that countless similar objects likely pass through the solar system unnoticed. The inability to track or study them in detail undermines humanity's capacity to understand its galactic environment. Harvard researchers stress that until more advanced survey instruments are deployed, our view of interstellar matter will remain fragmentary. The unknown itself, amplified by insufficient observational capability, is a source of scientific concern. Finally, there is the philosophical weight attached to discoveries like 3I/Atlas. If such objects are natural, then they represent the building blocks of distant worlds, fragments of alien systems now drifting between stars. If they are not, then they may hint at technological civilizations beyond Earth, civilizations capable of engineering objects capable of traversing interstellar distances. Either conclusion reshapes humanity's understanding of its place in the cosmos. Harvard scientists fear not only the technical challenges of interpreting 3I/Atlas, but also the paradigm shift that may follow from its proper explanation. In summary, the fear surrounding 3I/Atlas does not stem from immediate physical danger. Rather, it is rooted in uncertainty about its composition, its trajectory, its origin, and what it represents for our understanding of the universe. For Harvard researchers, the object is a symbol of how little we truly know about interstellar space, and how much more there is to uncover. Whether it proves to be a simple chunk of ice, an exotic form of matter, or something far stranger, 3I/Atlas forces humanity to confront questions that reach beyond astronomy into the deepest realms of science and philosophy.